and the Dutch ice skating phenomenon, so on and so forth. Those are all really fits very, very well in terms of the magnetic history or the sun's light history or in respect to our Earth history itself. And the point is that we can not only confirm such a thing for the 17th century, we know also in a previous time there were many more weak solar magnetic activity periods actually. In fact, for the last 10,000 years, we have information like we may have seen a lot of this what we call the Maunder minimum-like sort of activities, many times over. Put it that way.
Okay, so hold 1 second here. I just want to chime in. Could it be said that we shouldn't narrow our focus if we want to understand climate? We actually have to expand the focus to include the sun, the magnetic field of the sun, and the stars, and in the context of climate, and that to not do that is actually a disservice to science. Is that correct?
Yes, I would really, with no doubt, support that statement. I'm sure David Legates would support that too, because this is what we call a basic research. Let's just not talk about the sun and the earth. Let's talk about the whole solar system. As we know that the coming and going of the ice ages, these are the stuff that we've been talking about, ice ages that come every 100,000 years or so for the past 2 million years, for example. And what causes that? In fact, the best possible explanation of that is explained by how planet Jupiter and Saturn, which are very heavy planets, how they perturb and changes our relative orbits of the Earth with respect to the sun. Like, for example, how much the tail axis of our Earth is actually going up or down, or how actually the orbits itself relative to the sun precesses, okay? And then how circular or non-circular the orbit is. And those are all caused by Jupiter and Saturn and a bit of Venus. So clearly shows you that you really need to understand the whole system in order to really try to figure out what is happening on the Earth itself. I mean, remember that to explain the ice ages, these are the only truly viable explanation for this ice ages explanation, because there is no other way in which that we can explain why we have this huge amount of mass of ice actually. As we all know that actually in New York or Boston itself, 21,000 years ago, you got basically a mile or 2 miles thick of ice actually laying over us. And then today, of course, we can live here. Let's go back, don't even have to talk about that long, right? 1,000 years ago, the Vikings were living in the Greenland, where they couldn't be living then right now, because there was just so much ice now, compared to, let's say, 1,000 years ago, where the Vikings was able to colonize southwestern and southeastern part of Greenland, right? Mm-hmm. And basic research are extremely important, of course, because most of these factors are sort of connected, and we need to understand each of these components very carefully, instead of just jumping to the conclusion that, well, for the rest of the future, if we don't cut the carbon dioxide emission, the whole planet is going to be ruined completely. That's just a very strange, non-scientific sort of argument.
David Legates, do you have anything you'd like to add to this?
No, I think Willie's making the argument very well. The argument is really that if we think that the climate system is driven solely by carbon dioxide, and that's the only driver of climate change, you really just don't understand how the climate operates. The climate system is really, really complex. We have spent a lot of money over the last 20 or 30 years to try to understand it, and what we realize is it's almost like the scales on an onion. You start to peel back, and just about the time you think you understand what's happening, then there are other systems involved that have feedback mechanisms that we never thought of, that really make the system a very delicate and intricate climate system. And so it's not just something where you can say, well, increased carbon dioxide, temperature goes up, storms will increase, and therefore that's the future of the world. It's really a really complicated thing, of which carbon dioxide is really a small player. A lot of people get caught up in the fact that we're changing carbon dioxide and that's a radiatively active gas, but the most important greenhouse gas is not carbon dioxide, it's water vapor. It exists in the atmosphere in much higher concentrations of carbon dioxide. It has a much faster overturning ratio, and when it precipitates out in the form of rainfall, it can be very important to human life. If we don't get rain for a long time period, or if you get too much in too short a time, then serious problems happen. And so that's one of the things that I think we really need to focus on, is not just simply carbon dioxide and temperature, but really how are the things that economically and politically and philosophically affect humans and life. It's not really mean global temperature. I mean, to steal a line from Tip O'Neill, all climate is local. The idea is mean global temperature affects nothing directly. Really what we want to know is how is the climate changing where people live. That leads into sea level rise discussions. That leads into discussions of floods and droughts, heat waves, and cold spells. That's more important of a discussion on how those things are changing than really how carbon dioxide is changing, because that's really the important component of the climate system that hits home to various individuals, not just simply what is the carbon concentration of the atmosphere and how does that relate to mean global temperature.
What affects the water vapor then, since it's also a very important thing to be looking at?
Well, it affects temperature as well, but it's not just the temperature of the globe, it's the instability of temperature. I mean, if you have a warmer surface and a colder atmosphere, you get a lot more vertical motion. We see that in summer afternoons where you get thunder showers, where a lot of water is evaporated to the surface, it gets moved aloft. You get condensation, you get precipitation, you get thunderstorms quite a bit. We get tropical storms and hurricanes, for example, in the Gulf of Mexico and other places around the globe that are driven by temperature gradients, by essentially things that are related to the differences between the fact that we have cold poles and a warm equator. And that global circulation starts the atmosphere in motion, and we get local perturbations and local fluctuations on that become increasingly.
What do you think the concept of the Earth's magnetic field? I interviewed Dr. Dean Bonley from Canada, who said that every 100 years we're losing 5% of our magnetic field here, and has an effect on a lot of things. I'm just wondering, in both of your respective areas of focus, do you think that the loss of Earth's magnetic field is impacting what we're experiencing with climate change in general?
I guess I'll just speak a little bit on this, if possible. This is Willie soon. I sort of do not like the phrase loss of magnetic field. It's basically just the magnetic field weaken, perhaps, and this is, of course, is related to what we think is generating the magnetic field on Earth itself. Is essentially related to this rotation and convection in the Earth core itself, which we know that the Earth core is essentially liquid iron that is actually flowing, right, in the inner maybe 2,000-3,000 kilometers. And these are just, I would say, a natural cycle of the system. And as to how that connected to the Earth and weather and climate system, I think it's a lot more speculation than we know. I mean, this is where the problem of true science are to be able to add to. And unfortunately, a lot of this speculation will not be very, very prudent in the sense of trying to gain further understanding. I mean, we do know, of course, there is this interesting, there's clear relationship between, the magnetic field of the Earth interacting with basically the wind that is coming out, the charged particle that is coming out from the sun. There's no doubt about that. We have that relationship that at least we can use that to try to understand the phenomenon of aurora, for example. And then short of that, we also do know that if the relationship should changes, one could affect very much the region of the upper air called the stratosphere, which is around 10 to 50 kilometers or so up there, where, it's the whole region there is extremely, I guess, would function mostly through chemical reactions, where most of our ozone reside. 90% of the world ozone reside in the stratosphere, 10% of it in the troposphere. So should those relationship changes, meaning the magnetic field of the Earth and the sun's solar wind changes the relationship, then of course we would have a chance of changing or modulating how the stratosphere changes itself. And then there are, of course, further work that need a lot more detail, of course, that been able to show that how the changes in the stratosphere could actually affect the weather and climate system on the Earth's surface itself. Essentially by changing, of course, what Dave was talking about this, what they call the overturning circulation of the atmosphere air itself, meaning that heat and warm air being transported, up from the equator and then moving towards, right? And by different mechanism, different processes, that those phenomena all should be studied. This is why it's extremely surprising when people were saying that, well, even if you can change the stratosphere, which of course is true, it has only 10% of the Earth mass and 10% of the Earth atmosphere mass, and then 90% of it is sitting in the troposphere, then, hey, you cannot imagine this tiny little 10% could actually push the system at the bottom, which is 90% of it. But unfortunately, I think there are evidence to be able to show that, yes, you can do that. Essentially, it shows that this upper 10% is actually be able to control how much the energy would be able to shed, its energy, the troposphere, will be able to give off its energy to space, essentially. So this little lid there can be also very, very important in terms of controlling the weather and climate system on the Earth's surface and the ocean surface.
I hear that there is more radiation penetrating Earth's atmosphere from space than ever before. Is that correct?
Sorry?
I have heard and read that we are seeing a higher degree of radiation coming in from outer space through our atmosphere than ever before.
It's very hard to define that because it depends on which layers, all right? There is no doubt that the sun's magnetic activity has been quite high, let's say in the 1980s and 90s, and then we're kind of slowly weakening now. And of course, there's speculation that we could go into another Maunder minimum, but then again, that's pure speculation, and I do not like speculation unless you have very, very firm scientific basis. I would say that in general is true and not true, so it depends on where you are, of course. Maybe Dave would add in on that.
No, I haven't really heard of it. I mean, it does make sense that I don't know what time scale we're talking about.
What I'm getting to is that there appears to be a very high incidence of skin cancer.
A lot of that is due more to changing social mores than to solar radiation. I mean, skin cancer has gone up largely because a lot of people spent more time outdoors, had a lot more free time, and in particular, we cover up less now than we did in the past. And so I think in a lot of those cases, there's more people, hence the small probabilities of occurrences result in more people getting skin cancer. I think a lot of that has to do with increase in free time and maybe less clothing, if you will, than anything to do with changing concentrations. I mean, the argument was made back when we were concerned over the ozone depletion. And essentially the ozone hole was really happening over the South Polar region. And the reason for that is you had a circumpolar vortex set up that essentially didn't allow you to bring in ozone, and you had depletion of ozone because ozone is very much a renewable resource. If we don't have oxygen or we don't have solar radiation, then you don't have ozone, but then again, you don't need it. The fact that we have oxygen in the atmosphere and solar radiation coming in would replenish the ozone, and so it was coupled with that people tried to read, well, depleting ozone must therefore lead to increasing skin cancers. And I think that was a bad correlation because a lot of it was shown not to be related to ozone where people live. Over North America, the ozone layer had not changed dramatically, and yet we have seen a lot of increase in skin cancer over the area. So clearly it couldn't be due to changing solar radiation, and it's really due to changing behavior.
What is the role of the ionosphere? How important is the ionosphere?
Kim, I'd like to take just one little step back. Please allow me a few minutes because I think it will be important. This is what, just to amplify on the point where Dave was trying to say about ozone. Since you were going into this increasing incidence of radiations, and then probably it's related to changing transparency, like less ozone, for example, so that you have more ultraviolet radiation of the sun coming in. This is a question, indeed, you come back to the question of what can an astrophysicist add to this sort of study of the Earth itself? I mean, think about this particular question that I'm going to ask. As we know that the world ozone, 90% of them reside in the stratosphere, then 10% in the troposphere. And we know that ozone in the stratosphere, people say is good because it's blocking out the ultraviolet radiation. And then in the troposphere or near surface, it's not good because ozone is bad for our lungs. But I say, well, let's forget all about it. Let's take all of it out from the atmosphere. This is actually a thought experiment in the sense of Einstein always says that we can do certain thought experiment if we can answer them, of course. It's not good to ask a question when you cannot answer them. One that we can answer is this one.
Okay.
What if we take all of them out? And then we ask ourselves, how long would it take if we come back at all?